Hello there, ATSEVS533 students. What do you know? It is the third lecture of Module 2 of our class this semester. We're continuing to talk about the physics of climate and the processes that are physically causing temperature changes in the Earth's atmosphere surface system. Now remember, we kind of started off with a diagram like this one that came from NASA, which depicted Earth's energy budget. And what we're trying to come up with is a way to understand, or even better yet, model the ways in which radiation is moving through the Earth's atmosphere and determining the temperature of the Earth's surface. And we built up these, well, I mean, they might seem a little bit complicated. They're quite simple linear models of how radiation could be moving through the Earth's atmosphere. This happened to be a simple two-layer model, sometimes called a two-stream model, although they're called two-stream models no matter how many layers they have. And we built up this system that had an idea where we were, making estimates as to how much each layer was transmitting different wavelengths of radiation. Shortwave and longwave was all we partitioned it out into. And we could come up with, based on that model, we could come up with an estimate of the flux of radiation at the surface of the Earth, and ultimately then, from Stefan Boltzmann's law, the temperature of the surface of the Earth. And some of our estimates were better than others, but we were clearly on the right track here. This was clearly the strategy it was going to take to solve these problems. And so, well, we said, most of the time when we develop these kinds of models, we work with more than two layers. We divide the atmosphere up into more and more little pieces that can be represented individually in the model. And there's no particular reason to limit ourselves to 2 or 3 or 4. It could be n layers of this model. Real models of the atmosphere that are part of the climate models that we're going to learn about in the third module of the course typically have on the order of a few dozen layers to them. They'll be a little bit more complicated than this basic model, but the general idea is going to be the same. But we're going to end up with, of course, then, a system of a couple of dozen equations in a couple dozen unknowns, which is way more complicated than what you learned in, high school. It's not an easy problem to solve, but solutions exist. There are techniques that can be learned in math courses with high numbers of grad students in them and so on to learn how to solve those kinds of equations. And in fact, that's what we do. We actually do solve those kinds of equations. But it opened up another whole set of problems. I mean, realistically, when we just had 1 or 2 layers to our atmosphere that we just sort of divided up into half or something, or just even had one single layer, I could make kind of at least a ballpark estimate as to what the transmissivity of that layer of the atmosphere was for long-wave radiation, or what the transmissivity of that layer was for shortwave radiation. Just sort of as a ballpark guess based on the numbers that we saw from those observations on that slide from NASA. But if I'm going to be doing that for an arbitrarily large number of layers, that gets hard fast. While I have a rough sense that, most of the radiation that is long-wave radiation from the surface of the Earth is going to get absorbed, not transmitted, by the atmosphere, I'm not sure how much I think it is through some arbitrary layer, right? If I divided the atmosphere up into, let's just say, 10 layers, how much do I think that third layer is absorbing? I don't really have any intuitive idea about that. There's nothing in my background that helps me make that decision. We're going to need some kind of tool to do that that's going to be making an actual estimate of what the transmissivity of each of these layers was. It's going to be based on things like how thick the layer is and how many absorbing bodies there are in each layer, like how many carbon dioxide molecules or methane molecules or whatever. And we briefly mentioned on our way through that on the other day in our lecture that that's going to be called Beer's Law. Beer's Law is a powerful tool in the field of electromagnetic wave transmission and so on that talks about how radiation moves through an attenuating medium. Attenuating as in, as the radiation moves through, it can be lost, like absorbed or something like that. So as the long-wave radiation moves through the gas, it can make it some distance through before some of it is being absorbed and so on. That's Beer's Law. It comes from August Beer is his name. He was a German physicist in the early 19th century. And it's sometimes more correctly referred to as Lambert-Beer's Law, because there was another scientist involved in such a thing. But anyway, Beer's Law is sort of the name that has stuck. And there are a number of ways to write Beer's Law, as often is the case with those kinds of rules. But I have one formulation for it up there at the top of this slide, where we're saying that in this way of thinking about Beer's law, it is about monochromatic transmissivity. T here being transmissivity, and that little lambda on it being a symbol for wavelength. It means at this wavelength. Because as we know, these different materials, like carbon dioxide or oxygen or ozone or whatever, will have different transmissivities based on the wavelength of radiation we're talking about. Ozone has a very low transmissivity for ultraviolet radiation. It absorbs almost all of it. Whereas ozone has almost 100% transmissivity to, say, visible light, a different wavelength of radiation. So we're going to be saying that this is a way of writing it in terms of transmissivity. It turns out we can rearrange this equation and do some other things. And just to be clear, that symbol I lambda transmitted and I lambda incident, I just got this notation off of some other textbook or something. I lambda is like the flux of radiation. I lambda incident is how much radiation hit the start of this layer of the atmosphere, or this beginning of this path that the radiation is going through. And I lambda transmitted is the flux of radiation that made it out the other end. So like if we're dividing the atmosphere up into these layers, each of which will have some thickness delta S, okay, the path that the radiation is going through will be delta S. A certain amount of radiation will be incident upon, let's just say let's do it from the bottom up. So like long wave radiation is being emitted by the surface of the Earth. Some amount of that radiation is incident upon the bottom of that layer of the atmosphere, I lambda incident, and then a certain amount of that radiation will be transmitted through a layer delta S thick, and the amount that came out the other end is I lambda transmitted. Okay, probably we could have come up with some better definition than this, but no matter what, better notation, shall we say, than this, but this is what was in a textbook we used a different semester in the physical meteorology class. Now, when I learned about Beer's law, I learned about it from a delightful professor from a foreign country who tried to draw an analogy between how Beer's law works and the game of like American football. And God bless him, he tried really hard, but he clearly had no idea how football works. But I liked the game that my professor invented. So let's try to invent a game that's going to help us understand how Beer's law works. What we're going to do is we're going to line up one team, which I have as these little circles here, all along some line of scrimmage. Like I've got them kind of here against the 50-yard line. And the point of this game is there's no ball or anything like that. Let's just have those guys run. And they're going to try to run over all the way to the end zone, which is some distance away, delta S. Okay? So it's not really very much like football at all, but I like the idea that they're all lining up. They are all incident upon the line of scrimmage. All those dudes are going to cross the line of scrimmage. How many of them are going to make it all the way to the end zone here? Well, along the way, let's have them encounter some blockers. There's some kind of guys in our silly game that we're inventing here who are some kind of defense, and their job is to keep the guys from reaching the end zone. Okay? Makes a measure of sense. Kind of a stupid game, but it would work. Based on just that information, we should be able to use something like Beer's law to figure out how many of our little guys there that are those circles would make it to the end zone. How many of them would be transmitted past the blockers and make it to the end zone versus how many of them would be absorbed along the way or, blocked or whatever. Okay. Well, one part of the story is going to be about how many blockers there are. Okay. Probably more strictly speaking, it'd be how many blockers there are per unit area. Right? And that would be a way of counting. The more guys there are there blocking them, keeping them from getting all the way across those delta S meters all the way to the end zone, the fewer of them are going to make it. Okay. Part of the story as to how many guys are going to make it to the other end has to do with how many guys lined up on the line of scrimmage in the first place. If in your game, for whatever reason you could change the number of guys that line up on the line of scrimmage and start running, well, the amount of them that are the number of them that are incident upon the line of scrimmage would determine how many guys make it to the end zone, right? If you had half as many guys lining up on the line of scrimmage, you would expect half as many of them to get to the end zone. If you had twice as many guys lining up on the line of scrimmage, you would expect twice as many of them to get to the end zone, and so on. Or maybe not. Maybe it's not that simple. Maybe it's not like half as many guys line up, so half as many get to... You'll have to decide. Part of the story, too, will be the size of those blockers who are trying to keep our team from getting from the line of scrimmage all to the end zone. If they're just a bunch of little guys, like these little X's here, they might be less effective at stopping the guys as they run from the line of scrimmage to the end zone. or they might be bigger and better, more effective. So depending on how, it's something like how big they are or how good they are at blocking our guys, that would be part of the story too. And finally, there would be one other factor that would determine how many of our guys are going to make it from the line of scrimmage all the way to the end zone, and that's how far they have to go. If delta S is farther from the line of scrimmage to the end zone, fewer of our guys are going to make it past all those blockers. If delta S is smaller, like if we're inside the 10-yard zone, 10-yard line, they might all make it. We don't know. So the farther they have to go through that, past all those blockers, the fewer that will make it. Well, this actually turns out to be intuitively kind of reasonable, and in fact is exactly how Beer's law works. I mean, my professor from India was actually very much on the right track of how Beer's law works. His knowledge of football left a little something to be desired, but his knowledge of the Beer's law was impeccable. Because we're going to say that instead of these guys running from the line of scrimmage to the end zone, we're talking about like photons of long-wave radiation or photons of short-wave radiation, whatever, that are going from, you know, the beginning of some path through a layer of the atmosphere to the end of it. It's going to be the amount that is incident. That's how many photons or whatever. That is the flux of radiation that is incident upon the start of the layer. How much of that is going to make it through and be transmitted out the other side of the layer? That is delta S meters away. Well, it's going to depend on a number of factors, like 1, how much radiation was at the start of that path. I lambda incident. If I have more radiation coming in from, let's just say, from the bottom of my layer, it's long-wave radiation being emitted by the ground, and it is incident upon the bottom of my layer, the more radiation there is incident upon the bottom, probably more will make it out the top of that layer. That makes good sense, right? And if you look at Beer's law, you can see, for example, let's look at Beer's law up there at the top of slide 19 real quick. See how we took it from being that form of transmittance, monochromatic transmittance is equal to I lambda transmitted over I lambda incident equals something. We just rearranged this and made it the amount transmitted. Now in that equation I have circled there. The amount that's transmitted is equal to the amount that is incident times e to the negative nb delta s. Okay, so the amount that is transmitted is equal to the amount that is incident times some factor. So they're linearly related. Doubling the amount of radiation incident upon the layer doubles the amount of radiation that is transmitted through the layer. Making it half as much radiation is incident upon the bottom of the layer makes half as much come out the other side of the layer. Okay. 2. Another factor that determines how much radiation will make it through our layer has to do with the number of blockers. In this case, the blockers are absorbing bodies, to use the terminology that comes to us from physics. Those, in our case, are probably greenhouse gas molecules. Carbon dioxide, methane, nitrous oxide, strangely ozone. Ozone is a greenhouse gas. Water vapor molecules, also liquid water drops in clouds. They're bodies, and there's a certain number of those little bodies per cubic meter of the atmosphere. That number is represented by N. N is the number of these bodies per cubic meter. Alright. Now another factor that we talked about when we talked about that game that my professor was inventing there was to talk about like the size of the blockers. Big guys and little guys and so on. In the same sort of way, we have something like the size of these blockers, like these greenhouse gas molecules that are stopping the long-wave radiation that is moving through our layer, but it's not really exactly their size. It's partly about how effective they are at absorbing. Part of it is literally their size, but also just how good are these molecules at absorbing long-wave radiation. So there's actually this number B, which is called the effective size of the attenuating body. It's actually an absorption cross-section. It's literally like how big of a target each of these molecules are. So something that's better at absorbing radiation is made bigger, is described as having a bigger absorption cross-section, and something that is less good at absorbing your radiation is described as having a smaller cross-section. It's a combination of physically how big the molecules are and a factor that describes how good they are at absorbing radiation at that particular wavelength anyway. Okay. This is a pretty neat trick. This cross-section here is not just the physical size, it is a weighting that describes how effective they are, basically. I forgot I had a particular slide that actually said that. Then, factor that's going to determine how much radiation gets from the beginning of our layer to the end of our layer as it passes through that layer is just physically how far that is, delta S. If our layer is smaller, a greater amount of the radiation is going to make it through, and if our layer is wider, less of the radiation is going to make it through. So there's a delta S in there, in our form of Beer's law that we have circled up there. So this is our Beer's law. This is a very powerful tool for lots of things, from remote sensing to radiology, like if you go and you get a CAT scan or an MRI or something like that, to atmospheric physics and climate science. This is a very powerful tool for describing how radiation moves through some kind of attenuating medium. It explains how much radiation makes it out after a certain amount of radiation gets into a layer or a path or whatever you want to say. Now, before we get any farther on that, let's answer 3 quick questions about this. The first of which actually comes from a previous semester's exam 2, I think, actually. And in that semester, I asked this. In Beer's law, there was a symbol N, which is a symbol for A, the number of layers in our model, B, the number of absorbers per unit volume, or C, the flux of shortwave radiation incident upon the top of the layer of the atmosphere. Which one of those is what N meant in Beer's law? We've actually seen N a couple of times already since the beginning of this module. We better know which one is what we mean in Beer's law. Make a choice from those 3 options and get a little feedback before you move on to question 2.